The central idea of combustion analysis is that while it can be really nice to get a problem in chemistry where the mass percentage or the masses themselves are given to you, the reality is that chemists have to conduct experiments in order to obtain this information. And so, for the last part of today's lecture, I'm going to teach you one common technique that's used to do what's called elemental analysis, or to figure out how much of each element is present in a compound. And this common technique is called combustion analysis. And so, here's the basic idea of combustion analysis. We're going to combine together two different ingredients. One is some excess oxygen, which we can get pretty easily from the air. And then the second ingredient is the unknown compound that we want to analyze. And typically in combustion analysis, that compound is going to have probably some amount of carbon, some amount of hydrogen, some amount of oxygen, and maybe some amount of nitrogen as well. But we don't know what the mole-to-mole ratio is for any of these elements. However, what's really neat about combustion analysis is that present is a water absorber. And so all of the hydrogen in the compound is going to chemically react to form water. So all hydrogen in the compound reacts to form water. In other words, water is a compound that we can analyze after the combustion analysis is done to figure out how much hydrogen must have originally been present in the system. Similarly, part of the reaction is that all carbon is captured and reacted to form carbon dioxide. So once again, we have a way of trapping all of the carbon that's present, storing it in the form of CO2, and later, once we extract out how much carbon dioxide formed through the combustion reaction, that helps us determine how much carbon must have been originally present in the sample. And then last but not least, in some flavors of combustion analysis, you might also be able to react the nitrogen. And in that case, all the nitrogen reacts to form molecular nitrogen, N2. Now, what's kind of a bummer about our combustion analysis is that because there's excess oxygen at the start and at the end of the reaction, we're going to have to use a more indirect way to determine how much oxygen must have been present in our original sample. We can't use the amount of oxygen in H2O or the amount of oxygen in CO2 because, again, we can't guarantee that all of the oxygen is forming H2O or CO2. And so let's do a practice problem to see how this information can be used to determine an empirical formula. So here's a practice example. Let's consider caffeine, which we know is a stimulant. You probably might be drinking some right now as you're listening to this lecture video. It's known that caffeine contains 4 elements: carbon, hydrogen, oxygen, and nitrogen. So if we do a combustion analysis of caffeine, we can determine what caffeine's empirical formula is going to be. And so here's what happens. We combust together 1 milligram of caffeine and find out that it produces 1.813 milligrams of carbon dioxide, 0.4639 milligrams of water, and 0.2885 milligrams of N2. Using this information, let's try and determine the empirical formula. And I think a really good place to start is to reflect back on some of the simpler problems we did at the beginning of lecture. Our central goal in those problems was to determine our mole-to-mole ratio, and that's what our empirical formula is. But in order to capture that information, the first thing we wanted to do was determine how many moles of carbon were present in the sample, how many moles of oxygen, how many moles of nitrogen. And so if we could find a way to determine that information, we'd be well on our way to using our previous strategies to solve for the empirical formula. And that's exactly what we're going to do. Our key is going to be to understand that all of the hydrogen in the original compound was produces water, and all of the original carbon in our compound produces CO2. Okay, so if we have 1.813 milligrams of CO2, we know, or we can calculate the molar mass of CO2 and do a mole-to-mole conversion in order to figure out how many moles of carbon must have been present in the original sample. And so along those lines, this is going to start to look like yet another unit conversion problem. We're just going to add on one additional step. So first things first, let's write down a couple of our molecular weights. So our molar mass of CO2 ends up being 44.01 grams per mole. For water, our molar mass ends up being 18.01 grams per mole. And for N2, we get 28.02 grams per mole. Again, all that information we can determine from the periodic table in order to calculate our molar masses. So if we start thinking about the carbon dioxide, we know, or rather we can calculate, that all of the carbon dioxide, which ends up being 1.813 milligrams over 1, to start off with, we can convert that to moles by using our grams to mole conversion. So it's 44.01 grams of CO2 per 1 mole of CO2. Notice that I started off with milligrams, so I'd better do a conversion from milligrams to grams as well, so that I'm on track with my units. And pausing right here, we see that I'm now in moles of CO2 at the moment. This is where we're going to use our fact about combustion analysis to figure out how many moles of carbon atoms that corresponds to. And the trick is to recognize that for every 1 mole of carbon dioxide, I have 1 mole of carbon atoms. Again, that's because of the molecular formula of CO2. If I was talking about oxygen, there's 2 moles of oxygen atoms for every 1 mole of carbon dioxide. But for carbon, it's pretty simple. 1 mole of carbon dioxide is equal to 1 mole of carbon atoms. And so we can incorporate that into our unit conversion by saying that 1 mole of CO2 gives rise to 1 mole of carbon atoms. Once we carry out the math on this, we find that carbon is present in, there we go, 4.12 times 10 to the negative 5th moles. And again, put a little C here to remind myself that I'm in units of moles of carbon. We can do a similar process to figure out how much hydrogen is present by again reflecting that all of our hydrogen got stored in this water product. And so thinking about my moles, or rather my milligrams of water, I can convert to figure out how many moles of hydrogen atoms are present. So starting with milligrams of water, I'm going to first convert grams to moles. Next, I'm going to remind myself to do a milligrams to grams conversion. Some of you may have done this step first, and that's totally fine. And then last but not least, I want to recognize that for every 1 mole of water, there's 2 moles of hydrogen atoms present. Again, I'm getting that information from the stoichiometry. H2O tells me that there's a 2-to-1 ratio of how many atoms there are of hydrogen per molecule. I'll do a quick unit check and notice for myself that we're currently in our water canceling out, milligrams canceling with milligrams, grams with grams, moles of water with moles of water, and I'm left with moles of hydrogen atoms. So again, once I plug this into my calculator, that's going to help me determine that I have 5 times, gotta carry out my decimals, 5.15 times 10 to the negative 5th moles of hydrogen. Let's see if you can carry out the amount of nitrogen atoms or moles of nitrogen atoms yourself. Keep in mind, in our combustion analysis, we're assuming, or what happens in the experiment is that all of the nitrogen in the original compound is converted to molecular nitrogen, N2. So pause the video and see if you can figure this one out yourself. Okay, so how we want to handle the nitrogen is in the exact same way that we handle carbon dioxide and water. We know that we're starting off, or rather, the products of our combustion analysis were 0.2885 milligrams of N2. I'm going to use my molecular mass to convert from grams to moles. I'm going to remember to take care of my milligrams to grams conversion. And then pretty similarly to how it worked with water, we know that for every 1 mole of diatomic nitrogen, we have 2 moles of nitrogen atoms present. Carrying that out in my calculator, I figure out that I have 2.06 times 10 to the negative 5th moles of nitrogen. So that takes care of 3 of my 4 elements, but before I can determine the full empirical formula, I need to figure out how many moles of oxygen are present. And so what's really good to note in this case is that we know, and the fact we haven't used yet, is that we have 1 milligram of total compound. That tells us that whatever grams are not accounted for by the fact that we know how many moles of hydrogen, carbon, and nitrogen are present, we can convert that back to grams. Whatever we didn't take care of, whatever is lacking in that 1 milligram, must be due to oxygen atoms. And if we can figure out how many grams of oxygen are present, we can also figure out how many moles of oxygen are present. So let's go ahead and do that. I'm not going to show the math for this too much, but I will show it to you for one element. And we're going to do some gram or moles to grams conversions. So if we're starting off with moles of carbon, I know that for every 1 mole of carbon, there is 12.01 grams of carbon. Our masses are given in milligrams, so I think I want to do one last grams to milligrams conversion. And that's going to tell me that the amount of carbon present in my system is 0.4948 milligrams. A similar process is going to help me determine that I have 0.0519 milligrams of hydrogen. I have the amount of nitrogen that's given in the problem. Turns out all the nitrogen is nitrogen, so without doing any math, we can already determine that we have 0.2885 milligrams of nitrogen present. And so taking those three numbers subtracted from 1 milligram tells us how much oxygen we have. Minus all of this other stuff. And overall, that's going to tell us that we have 0.1648 milligrams of oxygen. All right, we're getting real close to our final answer here. The very last step that we need to do is do a grams to moles conversion for oxygen. Remember, in this case, we're starting off easy with just the amount of oxygen atoms in milligrams. And so I'm going to use my milligrams to grams conversion, and then also the molecular weight of oxygen, which happens to be 15.999 grams of oxygen for every 1 mole of oxygen. And that's going to help me determine that the number of moles of oxygen that I have is 1.03 times 10 to the negative 5th moles. And so let's remind ourselves of all of the moles that we determined. This many moles of carbon. And now, to get my final empirical formula, I just need to figure out what that mole to mole ratio is going to be. So I'm going to start off kind of messy. Carbon was 4.12. Again, I'm not going to write the factors of 10 to the negative 5th because I know they're going to cancel out when I divide by the smallest number. Hydrogen, we had 5.15. Nitrogen, we had 2.06. And oxygen, we had 1.03. Dividing all these quantities by the smallest amount, which happens to be 1.03, what we get is C4H5N2O. And so that was a challenging amount of work, right? However, this is the actual process that chemists have to go through in order to determine the empirical formulas that we're interested in. And so hopefully you can see with combustion analysis how it is that we can use a real experiment to determine empirical formulas, in this case, of a molecule that we all kind of know and love. I expect that it will take a couple of instances of doing a problem that involves combustion analysis before you feel totally comfortable with the process. And that's okay. It's fine to take a problem and then watch through this video a second time, step by step, to make sure that you can do this process yourself on a different type of molecule. But in the meantime, I'm going to end us for today with a few takeaways. Our takeaways is that we learned how to calculate both empirical and molecular formulas. For empirical formulas, we're really always trying to calculate the relative molar quantities of each element of a substance. And so working backwards, if we want to get to the molar ratio, we have to get to, as an intermediate step, figuring out how many moles there are of each substance. But the process of getting there can be different depending on what information that you're given in the problem. Sometimes you might be given the mass of each substance. If that's the case, we can use our molecular masses directly to go and do a mass to moles conversion and get our final answer. if we're given a mass percent, the first step that we need to do is assume that we have 100 grams of a compound to make the math easy, and then once again, just do a mass to moles conversion. And if you're given combustion analysis, we can use dimensional analysis and information about how all of, for instance, the carbon turns into carbon dioxide and all the hydrogen turns into water to help us determine how many moles of each atom were present in the original compound. And again, that process is always trying to route through how many moles are present in each substance. So if you're feeling stuck on a problem, that's always a really good place to start. How do I get to moles in this instance? Our second takeaway for today is that once we've determined the empirical formula of a compound, we can go a step further and determine the molecular formula, assuming we have additional information about the molecule. And in particular, we need to know the molecule's molecular mass, which we can figure out by doing, for instance, a mass spectroscopy experiment. All right, so that's all for today. I look forward to seeing everyone in class where we can practice some of these concepts together as a group. Until then, take care.